Yeah, thank you, Mark, for the introduction. And thanks also to Aaron and Astrid for organizing the seminar series and giving me the opportunity to present our work here. So as Mark said, I will talk about the effective action and black holes in asymptotic safety. And this talk is based on our recent paper here together with Jan Pawlowski from Heidelberg. Let me start with a brief overview of what I want to talk about. So I'll start with a brief introduction on black holes and asymptotic safety in general, just to set the stage. Then I will talk about the effective action, gamma, and present you two expansion schemes, namely the curvature expansion and the vertex expansion. And in particular, I'll show you how to relate these two expansion schemes. And then in the third part, I will come to black hole solutions, and I'll show you the effective field equations for our effective action. And I will talk about three different types of spherically symmetric solutions. And I'll close with a brief summary in the end. So to begin, I want to show you these two pictures that you most certainly have seen before. So here on the left, I'm showing you the Event Horizon Telescope image of the galaxy of the supermassive black hole in the galaxy M87. And on the right here, I'm showing you the data of the first gravitational wave detection of the LIGO and Virgo collaboration. And I'm just showing you these two images to remind you that black holes are no longer just like a theoretical construct that we can treat with pen and paper, but we are actually collecting data, and we are collecting data on the high curvature regime that hasn't been accessible before. So now the question is how are black holes described and how do we modify them? Now in the classical theory in Einstein's GR, black holes are described as solutions for the metric g mu nu of the vacuum Einstein field equations. So this could be the Schwarzschild solution or the Kerr solution for rotating black holes. But we know that these descriptions in classical theory are incomplete. So in particular, we have most prominently curvature singularities at the origin. But also in the rotating case, we know that the interior seems to be unstable. And when coupling these classical geometries to quantum fields, we also get the information problem from Hawking evaporation. So we know that this classical description is incomplete. But the hope is that when we include quantum fluctuations, the picture might change. And from quantum field theory, it is known that quantum fluctuations introduce a running or scale dependence of the coupling constants of the theory. So in gravity, the hope, or maybe the expectation, is that including these fluctuations will lead to a weakening of gravity at high energy scales, and therefore in the high curvature regime, and maybe resolve the discrepancies in the classical theory. So a natural question to ask is then, are there any quantum or other corrections that may be observable for black holes with the data we have available today? And in order to answer this question, we require a concrete prediction of a quantum gravity theory like asymptotic safety that we then can compare with the data. So the idea of this talk is to show you a way to compute such a prediction. And of course, this is the asymptotic safety seminar series, so you're all familiar with the topic, but just for completeness, let me give you some key points on asymptotic safety. So the idea of asymptotic safety is that gravity can be described as a quantum field theory that is non-perturbatively renormalizable. And at the heart of this paradigm, or of this idea, is an ultraviolet fixed point. So a fixed point at high energies where quantum scale symmetry is realized. And at such a high energy fixed point, the beta functions of dimensionless couplings, denoted here by beta gi, have to vanish by definition. And this then in turn implies for these dimensionless couplings gi that they attain a fixed value, a constant value in the ultraviolet. In turn, for dimension-full couplings, like the Newton constant, we expect them to scale according to their mass dimension. So for the Newton constant with mass dimension -2 in 4 dimensions, this would imply something like Gn scaling as 1 over p squared. Now I've put quotation marks here because we will treat the Newton constant, of course, in more detail later. And finally, we require such a fixed point to have only finitely many relevant directions because these correspond to free parameters in the theory, and this will result then in predictivity of the theory. Let me just show you what asymptotic safety looks like, or how it manifests in our setup. So here I'm showing you a flow diagram in the plane of 2 couplings. Namely, I'm showing you the dimensionless couplings of a 3 and 4-graviton scattering vertices. And you see here on the top, this red dot is the fixed point we are considering. We have indicated by the 2 black arrows 2 relevant directions. And you can see we can have trajectories that start here in the ultraviolet at this fixed point and flow down to the classical regime down here. And 2 such trajectories could look like this. So if we solve the flow for these two couplings at vanishing momentum, here I'm plotting the dependence on K. So this is the infrared cutoff scale of the FRG. You see that in the ultraviolet at high values of the cutoff scale, at high momenta in a sense, these couplings go to a constant value. And here in the infrared, they behave classically. So they go to the same value and go as K squared. Now, of course, bringing together these two concepts, black holes and asymptotic safety, is not a new idea. So the first papers on this topic that I know of are around the 2000s already, and there's been a lot of work in between. So I'm referring you to these two recent reviews that cover a lot of the material that has been produced in between, indicated here by the dots. And what is usually done in the literature is the so-called RG improvement. So this idea works by taking a classical solution for the metric, for example, the Schwarzschild metric, then taking Newton's constant, Gn, and promoting it to a scale-dependent function, g of k, where this k, again, is the infrared cutoff scale of the FRG. And then you take this RG scale and identify it with your points on a manifold somehow by some scale setting procedure. And this identification can be done in different ways, for example, by taking proper distance integrals or on the basis of curvature invariance. And in all these studies, there's a common theme. And so it seems there are hints that the classical singularity can be resolved within asymptotic safety. So this is a promising feature of these studies. And there are also hints that at the end of the evaporation process, there could be cold remnants. So this would, of course, have implications for the information problem. However, in these studies, one has to note that the scale identification, the scale setting procedure, is ambiguous. So there's no clear-cut scale identification in gravity. Furthermore, what's usually done is taking this infrared cutoff scale K, which is, however, a priori artificial. And what one should really consider is the momentum dependence, so the P running, or if one wants to be more precise, the dependence on the Laplacian or D'Alembert operator here. Furthermore, in the RG improvement, we take a classical solution that we improve, and therefore by construction, the solution is restricted by Einstein's equations. So in particular, for example, for the Schwarzschild case, the two metric elements in the time and radial components are related by this equation. And in the parameterization that I will later use, this corresponds to these two functions, f of r and g of r, being equal. So this are these two metric elements. So in order to go beyond, take one step beyond this RG improvement, our approach in this paper and in this talk looks like this. So we start by reconstructing the quantum effective action, the full quantum effective action at k equals 0, so at the physical vanishing cutoff scale. Then we perform a variation of this effective action to derive the effective field equations that will then correspond to the quantum version, basically, of Einstein's equations. And then we look for solutions to these effective field equations. And these solutions would then constitute these genuine quantum geometries that correspond to the black holes in the full quantum theory. So this strategy or this approach is what I want to line out in the rest of the talk. So let's start by discussing the effective action. So what I want to first show you is the curvature expansion. And here we start from the classical Einstein-Hilbert action of general relativity. And of course, as you know, it looks like this. We have Newton's constant sitting here up front, and we have the Ricci scalar, and if you like to introduce it, also the cosmological constant. And I'm taking away the minus sign here from the determinant already, because for the FRG part, we will treat the theory in Euclidean signature. And then only at the end, when we come to the black holes, we will perform a Wick rotation to go back to Lorentzian signature. And now in a curvature expansion, this term is usually taken as the first order term in an expansion. However, in order to generalize this, we need to consider one thing, namely the Newton's constant, as I said, has mass dimension -2 in 4 dimensions. And this means this classical term with just Newton's constant and a Ricci scalar cannot be present in this form in the ultraviolet, because there, by construction in asymptotic safety, we are in a scale invariant regime, so we cannot have any mass scales present. But simply taking Newton's constant and promoting it to a function of the Laplacian, so this would be the generalization of momentum dependence, in this classical action would only result in a boundary term. So we need some way to construct an operator that generalizes this term while avoiding these two problems. And this is the ansatz we take in the following for the effective action. So we take the classical action and generalize to the quantum effective action, where all fluctuations are integrated out. We then introduce this operator, curly r here, which is introduced to generalize the classical term, and we allow for dependence on the Laplacian and the curvature scalar. And then as second-order terms in this curvature expansion, we introduce these two second-order terms with the Ricci scalar squared and the Ricci tensor squared. And in between, we have these two functions with a dependence on the Laplace operator. And these functions, fr squared of Laplacian and fr mu squared, these are called form factors. And again, they generalize the idea of the momentum dependence or the running of coupling constants to curved spacetime. Now, there has been a big program in the last years to compute and describe these form factors. And I refer you to these two reviews here for general treatment of form factors in asymptotic safety, and to this paper down here, where it's been treated in the fluctuation approach and in the vertex expansion specifically. Now, let me also note that these form factors are quite a useful tool to compare the predictions between different approaches to quantum gravity, because a priori this parametrization of this curvature expansion is quite general, but the precise shape and dependence on this Laplacian here of these form factors will depend on the ultraviolet theory. So it's important to compute these in asymptotic safety in order to make a prediction. So now the question is, how do we compute these functions? And to this end, of course, we use the FRG, the functional renormalization group. And in the FRG, we consider a scale-dependent version of the quantum effective action, which is denoted here by introducing this infrared cutoff scale K. And I'm indicating here by these two arguments that we split the full metric into a background and a fluctuation part. And then, of course, we have the flow equation, Wetterich equation that we all know and love to compute the effective action. And it's given here in terms of the graviton loop denoted by the two blue lines and the ghost contribution in red dotted. Now, the approach is to compute this full effective action, solve basically the flow equation, and then take the limit to k equals 0, so at the physical cutoff scale, and set the fluctuations to 0. And then what we end up with is this object gamma of g, which is the full diffeomorphism invariant background effective action. And this object, its gauge invariant, is at the physical cutoff scale. So this object gamma g here contains the full physics, so the full information on the quantum black holes that we are interested in. So now we want to compute this gamma g in the parametrization of the curvature expansion that I showed you before. However, we need some approach to actually solve the flow equation. And to this end, we use another expansion scheme, which is the vertex expansion. And in this vertex expansion, we expand the full effective action about a fixed background. And for technical simplicity, we choose a flat background here. And then just written schematically, this expansion looks like this. So we expand the full effective action in powers of the fluctuation field H here. And the dots denote the vertices. So here we start with the background action, then the equation of motion, the inverse propagator, and then we have the 3-point function, 4-point function, etc., and higher. We parameterize the vertices, in particular here the background vertices, with a full momentum-dependent coupling, gamma g. And we have a separate coupling for each order n, for each vertex. And we allow for general momentum dependence here. And then we have a set of tensor structures, curly T here. And in the practical computations, let me note that we approximate this full set of tensor structures only by the ones generated by the Einstein-Hilbert action. But the information on higher curvature invariance is still present, namely here in the momentum dependence of these couplings. And now I told you we expand the effective action in fluctuation vertices, but for the reconstruction of the background effective action, we want these background endpoint functions. So we use an approximation for the full Nielsen identity exactly to relate the background and fluctuation endpoint functions. And our approximation looks like this. So here on the left, we have the background endpoint functions, which we obtain by n functional derivatives with respect to the background metric. And they are related to the fluctuation endpoint functions by this factor of the fluctuation wave function renormalization and this factor g here. And this factor g is defined as the classical Newton constant divided by the background graviton wave function renormalization. So this can be understood basically as a definition of really a running or momentum-dependent Newton constant. Now for reviews and on the whole fluctuation approach and in the vertex expansion, there are two nice reviews here, which are linked down here. So this is what it looks like. This is what it looks like when we insert our vertex expansion into the flow equation. We get a set of flow equations for the endpoint functions themselves, given in terms of the higher endpoint functions. So this has been set up already in this paper down here in 2016 or published in 2018. And what we do in this work, we for the first time solve the flow of the 4-point function. So we integrate this set of diagrams here from the ultraviolet fixed point down to k equals 0 to obtain the physical momentum dependence of the 4-point function. And this is what the result looks like. So here in blue, I'm plotting the coupling of the fluctuation 4-point vertex. And in orange, I'm plotting the same result for the 3-point vertex. As I said, this is at k equals 0. So this is the physical momentum dependence down here. And we start from the left. Here we see in the classical regime, those couplings go to 1. So in natural units, we recover Newton's constant here, so the classical theory. And in the ultraviolet, starting around here, around the Planck scale, these couplings scale is expected due to their mass dimension. So the 4-point coupling vanishes as 1/p², whereas the 3-point coupling goes as 1/p. And one interesting fact to notice, which can be seen nicely here in the inset, which is the same data just plotted linearly, you see that the 4-point function starts to scale in this fixed point regime approximately 1 order of magnitude before the 3-point function does. So around 1 order of magnitude below the Planck scale already. And as I said, we computed the 4-point function here, and the data for the 3-point function has been computed in this paper down here. And we use it to construct this fluctuation coupling. Okay, so now we have the momentum-dependent 3-point and 4-point function, but I told you we are interested in reconstructing this curvature expansion. So how's the relation here? So let's start from the Ricci scalar and noting that it's constructed of the metric G itself and the first and second derivatives of the metric. So when we expand about a flat background, this means that the Ricci scalar contributes a p² term. And now if we study the flow of the 3 and the 4-point function, we can actually see that there are p² and p⁴ contributions. And this again lets us recover these contributions from the Ricci scalar and from the second order curvature terms. And this can be seen very nicely when looking at the flow of the 4-point function. And in blue, I'm plotting here the numerical result for the flow of the 4-point function. And in dashed, I'm showing you 2 plots with a p² and a p⁴ term. And you see the orange fit with the p⁴ contribution very nicely captures this behavior of the 4-point function, whereas the p² fit does not so well. So this is a clear indication that within our setup, we do generate these higher curvature invariants, and we have an overlap with these 2 curvature squared terms. So now the question is, how do we extract these explicitly? And to this end, we can use a projection, namely on the transverse traceless part. And this has the advantage that the tensor structure generated by a Ricci scalar squared only contributes for the 4-point function and higher. So for the 3-point function in particular, it drops out. So by computing the 3-point function, we can extract the information on the form factor for the Ricci tensor squared. And then in combination with the 4-point function, we also get the information on the Ricci scalar squared. So how does this look? How do we perform this mapping directly? So written very schematically, what we do, we take this projection on the transverse traceless part, and we also contract all the free indices with a projection on the curvature tensor also. And what I'm showing you here on the left is basically the 3-point function and 4-point function that we computed with the FRG in terms of the diagrams. And then we compare this to the 3-point function and 4-point function we would obtain by taking 3 or 4 functional derivatives of this parametrization in the curvature expansion, where we have the form factor expressions. And written a bit more explicitly, this is what this equation looks like. So we have these constants C appearing here from the projection scheme. These are just numbers. And then here on the left, we have these momentum-dependent couplings, gamma G for the 3 and 4-point function, with a p² coming from the Einstein-Hilbert term. And then on the right, we have the same structure with the constants, the couplings or the form factor terms, and the corresponding momentum dependence from the curvature terms in the curvature expansion. Now we can use this equation for n = 3 and n = 4 to extract concrete expressions for these form factors. And for n = 3, I told you the Ricci scalar squared projection drops out. And so this results in this expression for the Ricci tensor form factor, where again, we have these constants appearing here. And in particular, I want to draw your attention here to the gamma 3. So this is the coupling of the 3-point vertex that mainly determines the momentum dependence of this Ricci tensor form factor here. And then we can do the same thing for n equals 4. And here again, we have these constants appearing. Now the Ricci tensor form factor also appears. And most importantly, the coupling gamma 4 here for the 4-point vertex appears. So again, this tells us by computing the momentum dependence of the couplings of the 3- and 4-point vertices, we get the information on these form factor expressions in the curvature expansion. And by now inserting our numerical data for these couplings, this is what we get for the form factors. So in blue, I'm plotting the R² form factor, and in orange, the R-mu² form factor. And we see that in the infrared, so at low momenta, both go to constant values. And the same thing happens in the ultraviolet at high energies. And we also see that the R² form factor is always larger in magnitude than the same for the Ricci tensor form factor. And let me also note the Ricci tensor is plotted here as the absolute value, because in fact, this is negative, except for this little part here around the Planck scale. And just to give you some more intuition, we can do a simple interpolation between the constant values in the infrared and ultraviolet and write down an expression something like this, where now the GR² with a tilde is the ultraviolet value and the GR² is just the infrared value. And I'm writing this here in position space. So we do this construction in momentum space, and then going to position space, we see that we have this 1/1 plus D'Alembert or Laplace operator appearing here. And this tells us that by in these form factors, we get a non-local contribution to the effective action. Okay, so we now have the form factors for the R² and R-mu² terms, and what is left is to construct this curly R operator. And this is a bit more non-trivial to do. So we only require that it is consistent with the infrared and ultraviolet requirements. So in particular, in the infrared, we know this term should reproduce the classical term. So just the Einstein-Hilbert term. And infrared here refers to small eigenvalues of the Laplacian. And here and in the following, I will neglect the cosmological constant because we will not treat it for the black hole solutions. And in the ultraviolet at high energies, so defined as large eigenvalues of the Laplacian, we require this term to vanish because of the mass dimension of Newton's coupling again. And then we can write down, let's call it an educated guess, so some suggestive form that fulfills these two requirements. And this has this general shape where we have the Ricci scalar on both sides, and we have this 1/Laplace plus Ricci scalar structure. And again, here the coupling of the 3-point vertex appears. And we also note again, because of this 1/Laplace, this term is non-local. Okay, so now we have constructed the effective action. We have the curly R operator and we have the two form factors. And now we can go to solve the equations of motions resulting from this effective action. However, as I said, the form factors introduce a non-locality into the effective action. And this poses a problem if we want to use numerical techniques. This is quite hard to deal with in general. So what we instead do is focusing on the dominant infrared, so low energy contributions. And we can actually expand these form factor expressions to something like this. So we get a constant part and this first correction proportional to the D'Alembert operator. And you note that I'm writing here the D'Alembertian again, not the Laplacian, because we now go back to Lorentzian signature in order to capture the causal structure in the black hole spacetimes. And then by doing this expansion for the two form factors, we get this resulting infrared effective action. So we have here the classical term, just the Ricci scalar. We get these two curvature squared contributions. And what is novel, we also get these extra terms with the box in between. So these terms here are 6th order in derivatives. And as you see, we have the structure curvature, tensor, sandwiching, the D'Alembert operator. And let me, of course, also mention these couplings and the coefficients appearing here. They are determined from the form factors that we derived in the vertex expansion approach. So we know that this infrared effective action has an ultraviolet complete sort of completion in asymptotic safety. And our goal is to find black hole solutions, or in general spherically symmetric solutions to this effective action. So in order to do that, we need to derive the effective field equations. And just as a quick reminder, let me show you how we get those. So of course, we take a variation of this effective action. And in case we just have a simple Ricci scalar, we just get out the classical Einstein equations. If we now include these second order terms, this is what we get. So the field equations now still are made up of Ricci scalar and Ricci tensor contributions. But what you will notice, we have these two extra derivative terms here. So in just classical quadratic gravity, the equations of motion become fourth order. And then if we use our expansion for the form factors here and here, the equations then also include sixth order derivative terms. And now our goal is to solve these field equations numerically for spherically symmetric geometries. And in general, a parametrization of spherically symmetric metrics looks something like this. We have in the time and radial components these two functions, f of r and g of r, that are a priori undetermined. These are what we want to solve for. And what you will notice again, what I mentioned in the introduction, these two functions in general don't have to be equal, which is only the case when using Einstein's equations. So because we want to use numerical integration, we need something to set the initial conditions. And this we will do by using the weak field limit of the quadratic gravity part. And this has already been derived in the late 1970s by Stell in this paper. And these weak field solutions have this general form. So the first term here, 1 minus 2m over r, is just the classical Schwarzschild term. And then we have these two extra corrections, these Yukawa-like terms that decay exponentially. These parameters m0 and m2 here represent the masses of the spin 2 and spin 0 modes that appear in quadratic gravity. And the parameters s0 and s2, these are free parameters of the solution, like the mass. So our strategy is we start at some large value of some large radial value. We use this weak field limit as our initial conditions, and then we integrate the full sixth order equations of motion towards the origin. And so for concreteness, let us now focus on a case where we set the mass parameter and s2 to 1 and only focus on the dependence on s0. And when we do this, we obtain three different types of solutions. So let me walk you through what you're seeing here. We have these functions plotted, f of r and g of r, against the radius. And for comparison, I'm also showing you the Schwarzschild metric element for mass equal 1 Planck mass. And you see that at large radial values, by constructions, these functions approach the classical solution. But then as we come towards the high curvature regime, the functions start to differ significantly. And for the Schwarzschild solution, we get a zero crossing here, where the Schwarzschild metric goes to 0. So this marks the location of the event horizon at r equal 2m, so 2 in lateral units here. And this is also where the new solutions start to deviate from the classical solution. So let's take a look at the solutions one by one. We start with the type 1. These types of solutions are found when this parameter S0 is negative. And you see that in these solutions, the function g of r is always larger than f of r, which is opposite to the type 2 and type 3 solutions where f of r is larger than g. In these type 1 solutions, you see that f of r actually does not go to 0 at the classical horizon, but approaches 0 only towards the origin. The function g of r actually grows towards the origin, and this implies that there is no horizon, but the metric stays regular in the whole spacetime, because in the metric we have 1 over gr appearing. However, we don't have horizon, but towards the origin, the curvature scalar actually blows up. So we can look at this, compute this by looking at the Kretschmann scalar. And this actually diverges stronger than r to the minus 6, so stronger than in the classical case. And now the interpretation of this type of geometry would be some form of naked singularity, so a curvature singularity at the origin, which is not shielded by a horizon. And just to give you some physical intuition as to what these solutions imply, I'm plotting here some geodesics. So what you have here is the new type of geometry at the origin, and I'm basically just dropping a test particle here from the side towards the origin, and I'm varying the initial conditions here a bit just to show you different trajectories. And in the type 1 solutions, you basically see that the gravitational attraction is stronger than in the classical case. So here we would have a trajectory where in a Schwarzschild spacetime, the particle would escape back to infinity, but in these type 1 solutions, it actually is attracted towards the origin. And we can also have these unbounded orbits where the geodesics lead back to infinity, but you see the deflection is still stronger than in the classical case. Moving on to the type 2 solutions. These are found for positive values of S0 that are smaller than some critical value. And here in these geometries, we actually have a point where g of r goes to 0. And we call this a horizon, although it is not clear whether the function f of r does also go to 0. It does look like it. There are indications for it, but numerically, we can only resolve it to close to this horizon plus some numerical epsilon, because here the equations are ill-defined. But in order to differentiate the type 2 from the type 3 solutions, we can look at the sign of the first derivative of f here, and you see that it is growing. Now, if we can interpret this really as a horizon, then you see that this is larger than 2. So if this is horizon, it's further out than in the classical case. And this is actually different from what's found in RG improvement, where typically the solutions are more compact and the horizon is smaller than the classical case. And here I'm again referring just to the review where this is discussed. And why this is interesting is because now these two functions, f of r and g of r, obviously behave differently. So we could have something like a modified black hole, or if this f of r stays finite, something like a wormhole geometry, but where the two functions f of r and g of r are not symmetric. And again, to build some intuition, let's look at some geodesics. And here we basically have the opposite behavior as in the type 1 solutions. So we find that here, in the Schwarzschild geometry, a particle would actually fall towards the black hole, but in the type 2 solutions, this particle can escape back to infinity. But also, if you choose the initial conditions accordingly, we can have geodesics that end, so that reach the would-be horizon in finite proper time. And finally, we go to the type 3 solutions. And those are obtained when we have a very large value of S0, larger than a critical value. And here again, we have the situation that the function g goes to 0 at this location, RH. But now, as you can see, the derivative of the function f is negative. And it seems to be diverging towards infinity. Now, this might be interpreted as a curvature singularity at the horizon. However, when you compute the Kretschmann scalar, this actually stays finite here at this point. And again, we look at some geodesics. Here, starting from the left, we see that basically the gravitational attraction or the gravitational potential of these new solutions is weaker than the classical case. So here we have a trajectory where in the Schwarzschild case, a particle would fall into a black hole. But in the type 3 geometries, the particle can escape. But something interesting happens when we choose the initial conditions such that the trajectory leads towards this would-be horizon. And here, actually, the geodesic is reflected from this point. And you see it quite strongly here. Particle comes towards this new geometry and then is reflected back. And if we go back to the shape of the solution, this can be traced back exactly to this negative derivative of the function f of r in the time-like component. So these type 3 solutions actually seem to have a repulsive gravitational potential near this would-be horizon. So we can also look at the phase structure, so where these solutions are located in a plane of S0 and the mass parameter. And now this idea of a phase diagram has been discussed in the literature in the case of quadratic gravity. And this is what it looks like in our case with 6 derivatives. And we use this Hawking temperature parameter. This would reproduce the Hawking temperature in the classical case. And this is useful as a parameterization because, again, here this derivative of f appears. And the first type of solutions, the type 1 solutions with negative S0, they don't have a horizon. So here this parameter cannot be defined properly. And these would be down here in the phase diagram, so at negative values of S0. If we then go to S0 equals 0, this is this dark blue line down here. This would be where the Schwarzschild solution sits. And by the dark blue color, you can see that if this is really the interpretation of a temperature for the new geometries, we would find that these type 2 and type 3 geometries actually have a larger temperature than in the Schwarzschild case. Then down here in the lower right corner, we have the type 2 solutions. And we have the transition line here, denoted by this blue dashed line, where we go from type 2 to type 3 solutions. And then the type 3 sit up here for large values of S0. Now, I told you in the beginning that in the RG improvement, typically one finds indications for cold remnants. And there's a nice discussion on the thermodynamics of black holes in this paper down here. And there's a possibility that cold remnants would also be possible in this type of theory. So for an astrophysical black hole with very large mass sitting here in this type 2 solution branch, we could imagine something. So we could imagine they behave like a type 2 black hole and then evaporate away, lose some mass, and then move towards this transition line where actually the temperature would vanish. And then, of course, in order to determine the properties of these potential remnants, one would have to study the solutions around this phase transition line in more detail. But this is an interesting speculation at this point. And finally, in the beginning, I was talking about some observational prospects. So how could we test these new geometries? So one very interesting place to look would, of course, be the features of the shadows imaged in event horizon telescope images. And here in particular, one could look at the size of the horizon and the location of the photon rings, as these are determined by the zero crossings of the solutions. And the features of black holes in asymptotic safety, so for the event horizon telescope images, have been discussed in these two nice papers. And in the case of quadratic gravity, it's also been studied in this paper down here. Now, how one could in particular use the measurement from the shadow is by looking at the size of the horizon in this shadow image and inferring the mass parameter that would be given in case of a Schwarzschild black hole, for example, by the Schwarzschild relation for the event horizon, and then comparing it to the mass that one would obtain by measuring the orbital parameter. So if you have a star orbiting, for example, the black hole, and this would give you two estimates for this mass parameter, one at large radii, larger than the horizon, and one at radii close to the horizon. So by comparing the estimates you get from these two measurements, you could place then constraints on the parameters, so on the size of these parameters S0 and S2. Another interesting place to look in gravitational waves would be the ring down after the merger of two black holes. And here you would basically have a perturbed geometry, and this would then settle down into the ground state by oscillating in quasi-normal modes. And now we have a dynamic equation. So we have the equation of motion, and we, in principle, also have the solutions. So one could, in principle, study these quasi-normal modes in our new theory. And of course, gravitational wave echoes would also be a bit more exotic type of test that one could do. And here one would have reflections from any structure close to the event horizon. And this could potentially be interesting in these type 3 geometries where we have this repulsive gravitational potential at the horizon. Now, a word of caution when making such claims, of course, the corrections to the weak field metric are already exponentially suppressed. So when we have the masses of the new spin 0 and spin 2 modes of the order of the Planck mass and order 1 parameters S0 and S2, these corrections would probably not be observable for astrophysical black holes. So in turn, if we would want observable effects, we would either need very large parameters S0 and S2, or we would have to have these masses of the new modes very small. And this could be achieved by having very large couplings of these of the new curvature terms. So I'm showing you here the relation of the masses M0 and M2 to the couplings of the R squared and R mu squared terms. Now, potentially these features could be enhanced in rotating solutions. And again, I'm referring you to these papers where the effect in rotating solutions has been discussed, and there seem to be promising hints that also for smaller scales there could be some observable effects. And one final point, in our computations, we only considered gravity. So we only had pure gravity computations. So when including matter, the scale where the couplings start to scale according to the fixed point, according to the scale invariant fixed point regime, this transition scale could lower when including matter. So the scale where the new physics sets in could also be lower than the Planck scale. Okay, and with this, I'm already coming to my summary. So what have we done? We reconstructed the full quantum effective action gamma of g at vanishing cutoff k equals 0. And this we have done by computing the momentum dependence of the endpoint functions, so in particular of the 3 and the 4-point function. And here, as a reminder, I'm showing the plot where you see the momentum dependence of the couplings of the 3 and 4-graviton vertex with a classical regime in the infrared and this asymptotically safe scaling regime in the ultraviolet. Then we used this momentum dependence to compute the effects of higher curvature operators in the effective action. And I showed you this parametrization with the form factor expressions in this curvature expansion. And in the low energy limit of this effective action, we get classical term back, and we get the 2 curvature squared corrections. And in addition, also these 6th order corrections. And then these result in effective field equations, again, with 6 derivatives. And in these field equations, we looked for 3 different types. So we found 3 different types of spherical solutions, namely these type 1, type 2, and type 3 geometries. And I showed you some properties of these solutions. Okay, and with this, I'm already coming to my end and want to thank you for your attention. And I'm looking forward to any questions you might have.
Yeah, let's all thank Jan for the very nice talk.